This video is about Stokes' theorem, but I want to start off by reminding you what Green's theorem says. Green's theorem can be interpreted as a special case of Stokes' theorem. They say almost exactly the same thing. Now, in some sense, all of the fundamental theorems, the divergence theorem included, they all say the same thing at some level too. But Green's and Stokes straight up say the exact same thing. So it'll help to think about Green's theorem first. In the context of Green's theorem, we have a two-dimensional region in the plane, call it D, and we have some vector field f. And the statement of the theorem is that the double integral over D of the curl of the vector field, this is equal to the line integral of f along the boundary curve. Now, a couple comments. On the left-hand side here, the curl of f in 2 dimensions is a scalar valued function. It's just a number. So that means that this integral on the left is an honest double integral. So in other words, on the left-hand side, there's no issue about orientation or anything like that. However, on the right-hand side, this is a vector line integral, so the orientation of the boundary curve matters. And we know that the boundary curve is oriented so that the region D is to your left. So for example, on the picture I drew here, the boundary curve would be oriented like this. Anyway, that's Green's theorem. The double integral of the curl over the blob is the integral over the boundary curve. To get Stokes' theorem, we take this situation in 2 dimensions and just lift it up into 3 dimensions. So picture taking this blob D and just picking it up and let it flop around in 3 dimensions. If you do that and you account for everything correctly, that gives you Stokes' theorem. So the setting is we have a surface in 3 dimensions. This time it's an oriented surface. And on the left-hand side of Stokes' theorem, rather than the double integral of the curl, we have the surface integral of the curl. And then on the right-hand side, we're equating this to the line integral of the vector field over the boundary curve, just as in Green's theorem. So before I point out some details, just to say it in words again, the surface integral of the curl is the line integral of the vector field. Now, one difference here is that the curl of f, since we're in 3 dimensions, this is a vector field. So the integrand is vector valued, and what that means is that we're doing a vector surface integral. The reason why that's important is because we know that when we evaluate vector surface integrals, the orientation of the surface is important. So unlike in Green's theorem, where you don't have to discuss any kind of orientation of the blob D, in Stokes' theorem, your surface S does come with an orientation. The story is the same on the right-hand side, which is we have a vector line integral, so the orientation of this boundary curve is important. And the orientation is determined in roughly the same way as in Green's theorem. Pretend that you are the normal vector. So for example, in the picture I drew here, the normal vector is pointing up. So pretend that you're the normal vector and stand on the boundary curve. What direction do you have to walk in so that the surface is to your left? That's how the boundary curve is oriented. So in my picture here, it would look like I walk this way in order for the surface to be to my left. An orientation of a surface, in other words, a normal vector, determines an orientation of the boundary curve, and vice versa. Anyway, that's Stokes' theorem. It's Green's theorem just up a dimension, where the double integral part turns into a surface integral. And the last thing I'll say before we look at some examples is just like with Green's theorem, you can think about Stokes' theorem as being a two-way road. The fact that these two integrals are equal to each other can be beneficial in different ways. Sometimes you might be interested in a particular line integral, and it may be easier to instead compute the surface integral. Or sometimes you might be interested in some kind of surface integral, and it will be easier to compute the line integral. It really depends on the situation. In this first example, we're given a curve C, and we're told that it's the boundary of some surface S. This surface is defined by the equation y equals x squared plus xz plus z squared, and x and z are restricted as written. S is an oriented surface. It has orientation pointing in the positive y direction. And then the boundary curve C is oriented via the induced surface orientation, the thing that I just talked about. We also have a vector field F, and the goal of the problem is to compute the line integral of F over this curve C. Okay, so that was a lot of information. To process it, let me draw a picture and we'll think about what to do. So here's the three-dimensional world. This surface that we're given, it's probably going to be hard for me to draw it exactly, but to capture the main features, I recognize that the equation of the surface is y as a function of x and z. And these domain restrictions, x between 0 and 1 and z between 0 and 2, tell me that the vague shape of this surface is going to be a blob sitting over the xz plane, in particular sitting over the rectangle 0 to 1, 0 to 2 in the xz plane. So very roughly we would see something like this. Again, the shape probably doesn't actually look like this. What's most important to me right now is just the fact that y is a function of x and z, so it looks like some blob sitting above the xz plane. Next, we're told that the surface has orientation determined by a normal vector which points in the positive y direction. So in my picture, that would look like this. And then the curve C is the boundary curve of this surface with the induced boundary orientation. So what would that look like on the picture? Well, I pretend that I'm the normal vector, and I'm standing on the surface, and I walk to the edge. Which way would I have to walk so that the surface is to my left? I would have to walk this way. So there we go, that oriented curve is C, and ultimately that's the curve that we want to compute the line integral over. Now, as usual, I do this in pretty much every example that I do. We probably know from context that we're going to be using Stokes' theorem, because we're in the middle of a video all about Stokes' theorem. But in the statement of the problem, I have said nothing about using Stokes' theorem. It's up to us to make that decision. And at the heart of it, all we're supposed to do is compute some line integral. So the first thing we could consider is, maybe we can just compute it directly. But this seems hard for a number of reasons. One of those being the e to the z squared in the z component. Anytime you see something like that, integrating things directly is scary. The other reason is that if you wanted to do this, we would have 4 different segments of the boundary to parameterize. Because the surface is sitting above this rectangle in the xz plane, there will be 4 smooth boundary pieces corresponding to the 4 sides of the rectangle. And so you could maybe do it, but it would just be really annoying. You would have to compute 4 different line integrals. I don't really want to do that. Now, the other thing you might think is, well, it's a closed loop. Maybe the vector field's conservative. If it is, the integral would be 0. But I can kind of eyeball the curl, and I can see that the first component of the curl is not going to be 0. So therefore, I'd know that the vector field will not be conservative. In any case, because this curve is the boundary of a surface, we could use Stokes' theorem as an option here, and this might be easier. So let's do that. By Stokes' theorem, This integral that we care about, the integral of f over c, well, by definition, c is the boundary curve of S. So Stokes' theorem tells us that this integral is equal to the surface integral over S of the curl of f. So I'll compute the curl of f. Doing the cross product should give you the vector -1, 0, -1. And at this point, we just have a surface integral to evaluate. So we're done thinking about Stokes' theorem or whatever. We're just in the world of surface integrals. And how do you evaluate a surface integral? Your first step is to parameterize. So that's what I would do. And I'll use the fact that I mentioned earlier that y is a function of x and z. So one way I could get a parameterization, g of uv, is to say, well, I'm going to let x be u and z be v. And then for y, I don't have a choice. Y has to be u squared plus uv plus v squared. And the domain for my parameters comes from this domain restriction for x and z. U is going to range from 0 to 1, and v is going to range from 0 to 2. And there we go. We have a parameterization of the surface. Now, this is a vector surface integral, so the orientation matters. So what we need to do next is we need to check if the orientation is correct. I'll do that by computing the normal vector. Because I wrote g of uv, this means I have to take the derivatives in the order u cross v. So that would be this vector cross this vector. And if you compute the cross product, you get this vector. The question is this pointing in the correct direction? Well, we're told that the orientation of the surface is such that the normal vector is pointing in the positive y direction. And if I look at the normal vector I wrote down, the y component of this vector is -1. That means that this is pointing in the wrong direction. It's pointing in the negative y direction. So this is not oriented correctly. So to fix it, instead, I'll just consider the parameterization g of vu, which is the same formula with the same domain. If I do that, then my normal vector is going to be the cross product in the opposite order, which will give me the negative of the normal vector that I computed above. And this one will be oriented correctly. And now we just compute. So to recall what we've shown, the line integral that we care about by Stokes' theorem equals the surface integral of the curl. And then using our parameterization, we can take that surface integral and turn it into a double integral. As an iterated integral, we'll get the parameter bounds. The vector field is still -1, 0, 1. That doesn't change. And then I dot with the normal vector that we found. Multiply out that dot product. Simplify. Do some calculus. And there you go. In this next example, we're given a surface, but we're not actually told any explicit information about what that surface is. We're just given a picture. So the way to look at this picture is that the surface is this blue bag shape, and it has an opening at the top. The opening of the bag is given by the circle x squared plus y squared equals 1 in the xy plane. And the orientation of this surface is given by this purple normal vector, so it's kind of pointing outward. We're also given a vector field f, and the goal of the problem is to compute the flux of this vector field through the surface. Now, right off the bat, you can probably tell that we're going to have to do something clever, because there's no way for us to compute the flux directly, because we don't know what the surface is. It's just a picture. So there would literally be no way to parameterize the surface or anything like that. So we're going to have to do something. The main idea here is something called surface independence. This is a complete analog to path independence that we talked about when we discussed conservative vector fields. This is the same concept, just up a dimension. So what do I mean by this? Suppose S and T are two oriented surfaces with the same oriented boundary curve. So for example, maybe I have a surface in blue like this, S, and its boundary curve looks like this. And I could fill in this opening with another surface, T, such that the oriented boundary curve is the same. This is the scenario that we're dealing with. Then, what would Stokes' theorem tell us? If we had some other vector field G, Stokes' theorem would tell us that the surface integral over S of the curl of G, well, this is equal to the line integral of G over the boundary of S. But the boundary of S is the same as the boundary of T, so applying Stokes' theorem again in the opposite direction, this is the same thing as the surface integral of the curl of G over T. So in other words, the important equality is the thing in purple. If you have two surfaces and they have the same oriented boundary curve, the surface integral of the curl of a vector field is the same over both surfaces. This is the kind of thing that we want to use here. Now there's still some things to check, but this is the point. Ultimately, we care about the flux of F through this goofy surface. So if we can show that F has a potential, a vector potential, to be specific, then we could use surface independence and pick a simpler surface. That's the philosophy here. But the first important thing to talk about is exactly that we care about the flux of F and not the flux of the curl of F or something like that. We genuinely care about the surface integral of F. So somehow we need to show that F is the curl of G for some other vector field G. And the question is, do we actually need to figure out what G is? The answer is no. So the last fun fact that I need to remind you of before we actually do some math is the following. So this is an analog of the whole simply connected, curl zero implies conservative, etc., that whole stuff. Again, this is the same thing, just up a dimension. So here's the version that we'll use. If you have a vector field and it's defined on all of R3, and if the divergence is 0, it turns out that F has a vector potential. In other words, if the divergence is 0, and the vector field's defined everywhere, then there is some vector field G such that the curl of G is F. Don't know what it is, don't care in this case, we just know that it exists. Okay, so let's kick this into action. Here's our vector field. And the first thing I'll do is I'll use this fun fact in red to conclude that we are allowed to use surface independence. The first thing to observe is that F is defined on all of R3. That's clear. There's no issue with the domain. And then if I compute the divergence of F, I'll take the x partial of x plus the y partial of the y component plus the z partial of the z component, and we would get 1 minus 2z plus 2z minus 1. And that's 0. Okay, so the vector field is defined on all of R3. Its divergence is 0, so by that fun fact in red, F has a vector potential. There's some vector field out there, G, such that the curl of G is F. Again, we don't know what it is, don't care. All this means is that we are allowed to use surface independence. So from here, we just have to decide what other surface should we consider. We probably want to look for a surface which is much simpler than our blue bag thing, but one that has the same boundary as our bag. To me, I think the easiest thing that we could pick would be this disk. We could just fill in the unit disk in the XY plane. That's about the simplest surface that we could take that has the same boundary. So that's what I'll do. I'll let t be the unit disk in the xy plane, but we have to make sure that the orientation matches. The orientation of this disk needs to agree with the boundary orientation of the curve. If I look at the original surface and I think about how the boundary curve is oriented, pretend that I'm the normal vector and I stand on the boundary curve, I would have to walk this way in order for the surface to be to my left. So this boundary circle is oriented clockwise if you're looking at it from above, and our new surface needs to give the boundary curve the same orientation. So if you think about it, this would mean that the normal vector for t should point down, should point in the negative z direction. I'll say orient t so that this is the case. The normal vector needs to point in the negative z direction. If we do that, then the boundary of t is the same as the boundary of s as an oriented curve. I'll let you think about that for a second to make sure it makes sense, because this is the most important part. Now that we have a surface with the same oriented boundary, by surface independence, we can say that the flux of f through s is the same as the flux of f through t. And again, like before, now it's just a matter of computing the surface integral. I don't have to think about Stokes' theorem or surface independence or anything like that. We just have to compute this surface integral. How do we do that? We parameterize the surface. So no surprises here. A parameterization of the surface could be, for example, g of r theta is r cosine theta, r sine theta, and 0. Because the disk here always lives in the xy plane. Theta I could send from 0 to 2 pi. R I could send from 0 to 1. Then I could compute the normal vector. I'll take the r derivative cross the theta derivative. You'd get the vector 0, 0, r, which points in the wrong direction. This vector is pointing up, and I want it to point down. So instead, I'll reverse the parameters and consider g of theta r. I know that when I do that, the normal vector will point down. It will be the vector 0, 0, negative r. And then we just set up the double integral. If I plug in the parameterization to the vector field, I would get x is r cosine theta, sine of z squared is sine of 0, minus 2yz is minus 2r sine theta times 0. The third component is z squared minus z, which is 0 minus 0. And then I dot this with 0, 0, negative r. And this is pretty nice. The dot product is 0. So therefore, the integral is 0, and we are done.